I want to start today with a bit of a riddle.
Oh, okay. I love a good riddle.
It's a comparison that I think really exposes the cracks in the foundation of modern technology.
Let's hear it.
Okay, here it is. What is the nitty-gritty difference between the most advanced, cutting-edge AI we have today?
Something that costs billions of dollars to train.
Exactly. And, well, a common house cat?
That is quite the opener. I'm assuming you're not talking about the fact that one purrs and the other needs a massive server farm to cool down.
No, not the hardware. I'm talking about capability. I mean,
Yeah.
think about it. That AI can write a Shakespearean sonnet in, what, 3 seconds?
Right. You can code a website from scratch.
It could probably pass the bar exam with a higher score than most human lawyers. It is, by any standard definition, smart.
It handles data processing at a speed biology just can't match.
Exactly. And here's the thing. If you took that supercomputer and dropped it in the middle of a jungle, or even just changed the rules of its game slightly without telling it.
Like putting the chess pieces on a board with friction.
Right. It just freezes, it fails, it has absolutely no idea what to do.
Whereas the cat,
The cat lands on its feet.
it finds food, it sees shelter from the rain, it avoids predators.
It survives. It possesses something the machine doesn't. A drive to just keep on living. And that specific difference, that gap between processing data and staying alive, is exactly what we are diving into today.
It really is the holy grail of robotics and AI research. We're talking about moving from intelligence as a static tool to, I guess, aliveness as a dynamic process.
And we are looking at a fascinating research paper to guide us. It's titled Life-Inspired Interoceptive Artificial Intelligence. It's by Sungwoo Lee, Youngyun Oh, and a team of researchers who are really bridging that gap between neuroscience and engineering.
And their big idea is that maybe we've been building AI backward.
Or at least we've been missing a huge half of the equation.
We've been building brains without bodies.
Right. So the mission for today's deep dive is to see if we can bridge that gap. We're going to explore how giving an AI an internal sense of a body, literally making it feel hunger or stress, might be the key to true autonomy.
It's a fascinating concept. The sources combine cybernetics, neuroscience, robotics, reinforcement learning.
Yeah.
It really forces you to rethink what intelligence actually is.
Okay, let's unpack this. Because usually when we talk about AI, we talk about its output. But the authors here, they start by pointing out this massive flaw.
They do. They define the core problem with two specific concepts: autonomy and adaptivity.
Which sound a little like corporate buzzwords, but in this context, they mean something very, very specific. Right?
Very specific. So autonomy here isn't just working without a cord. It means the ability to choose your own goals based on your own needs.
And current AI doesn't have needs.
No. It has a task list given to it by a human.
So it's like a very efficient butler. It waits for an order, write me a code. And if no one gives it an order, it just sits there.
Precisely. It has no internal motor. It's reactive, not active. And then you have adaptivity. That's the ability to survive when the environment changes unpredictably.
The paper calls this the non-stationarity problem.
Right.
Which is a bit of a $5 word. Let's break that down for everyone.
It's just a fancy way of saying the world doesn't stay the same. In conventional AI training, you feed the system a data set, say millions of pictures of driving scenarios.
And it learns that data set perfectly.
But if the real world drifts too far from that training data, the lighting changes, the road surface shifts from asphalt to ice. The AI suffers from what we call catastrophic forgetting.
Catastrophic forgetting. That sounds incredibly dramatic.
It feels that way to the engineers. When the AI tries to learn the new rules, like driving on ice, it tends to completely overwrite the old rules for driving on asphalt.
So it's like studying for a history test, knowing everything about the French Revolution, and then being handed a math test. And in the process of learning the math, you instantly delete the memory of who Napoleon was.
That's a great analogy. You overwrite your previous competency. Living organisms don't do that. You don't forget how to walk just because you're learning to drive.
You have a stable core.
You add to your repertoire. You don't replace it. And the reason, according to this paper, comes down to interoception.
Okay, interoception. This is the star of the show. We hear about perception all the time, eyes, ears, sensors, but this is different.
It is. Most AI is built on exteroception. That's monitoring the outside world, cameras, microphones, lidars. It's all about answering what is out there. Where is the door?
It's outward facing, mapping the territory.
Exactly. Interoception is the process of monitoring the internal environment. In us, that's your glucose levels, your oxygen saturation, your blood pressure. It's the sensing of the self.
The source uses the concept of homeostasis here, and reading this, it made me realize how much we take our own bodies for granted.
We do. Living organisms have what they call essential variables. These are things that must be kept within a certain range, a viability zone.
If your temperature gets too high or too low, you die.
Right. These aren't preferences, they are non-negotiable constraints.
I came up with an analogy for this. It's the difference between a car and a body. A car has a gas gauge, right?
Uh-huh.
So it technically knows its fuel level. But the car doesn't care if it's empty. It'll just stop on the highway. It needs a driver to look at the gauge and say, oh, I need gas.
The car has sensors, but no autonomy. No drive.
But a body makes you feel it. You get hungry, you get thirsty, you shiver when you're cold. The goal of your life isn't some arbitrary score. The goal is just keep these internal numbers in the green zone.
And that is the critical shift these researchers are proposing. The primary goal in biology is maintaining homeostasis. Everything else, walking, eating, building a house, it's just a complex strategy to serve that internal balance.
So we need to stop giving AI external goals like score points.
And start giving it internal needs.
So instead of programming a robot to clean the floor, we program it to feel stressed if the floor isn't clean.
In a way, yes. We have to build a body in the machine, a virtual physiology.
This is where it gets really interesting for me, because the paper lays out a blueprint for how to actually code this. A piece of software doesn't have blood sugar.
No, it doesn't.
Yeah.
But the authors explain how to implement this mathematically within a Markov decision process, or MDP.
The standard framework for reinforcement learning, how we teach AI to play chess or Mario Kart.
Correct. But they modify it in 3 specific steps. This is the technical backbone of interoceptive AI.
Okay, walk us through it. How do you give code a body?
Step 1 is factorization.
Breaking things apart.
Exactly. In standard AI, all data is just state. A wall, your speed, the goal, it's all just one big bucket of numbers. The authors say you have to mathematically separate or factorize the internal state variables from the external state variables.
So you literally draw a line in the code. These variables are me, E, and those variables are the world.
You have to define the boundary of the self. Which brings us to step 2, creating the boundary, which is often called a Markov blanket.
A Markov blanket. Sounds cozy. I'm guessing it's mathematical.
It is. It's effectively digital skin. Think about it.
Mm-hmm.
Your internal organs are relatively stable. The external world is chaotic and noisy.
You don't want the wind blowing outside to directly change your heart rate?
Exactly. The Markov blanket ensures that internal and external states only interact sparsely through the boundary. It insulates the self from the chaos of the world.
So the chaos doesn't crash the system. It's like a firewall for your biology.
Correct. And then we get to step 3,
Mhm.
and this is the absolute game changer. Internal rewards.
This was the moment I stopped and said, whoa. Because in AI, the reward is always external. You won the chess game, plus 100 points.
It's a cookie from the programmer.
Yeah.
And the authors, quoting researchers like Singh and others, they flip that logic on its head. They state, all rewards are internal.
So let me make sure I have this right. The robot doesn't get points for opening a door. It gets points because its internal battery stress level is high. And opening the door leads to a charging station, which then lowers that stress.
Precisely. The reward isn't the charging station itself. The reward is the reduction of the internal drive, the distance from its homeostatic set point. The pleasure, if you want to call it that, is the relief of tension.
That changes everything about motivation. Now, the robot isn't opening the door because you told it to. It's opening the door because it wants to fix an internal problem.
It creates intrinsic motivation. If the robot's fully charged, it might ignore the door completely. It might go explore a new room instead, because maybe it has an internal drive for novelty that's now unsatisfied,
It chooses its own behavior.
based on its current state. Which brings us to the problem of choice. How does it decide what to prioritize? If I'm hungry and tired and curious, what do I do first?
This is the exploration-exploitation trade-off.
It's a classic problem. Should I stick to what I know works exploitation, or try something new to see if there's a better option exploration?
And usually engineers just hard code a ratio, right? Like explore 10% of the time.
Right, which is clumsy.
Yeah.
It means 10% of the time, the robot acts foolishly, just for the sake of it. Nature does it differently. And the source has a wonderful example here with the fruit fly, Drosophila.
I love this example. It's amazing what we can learn from a tiny fly.
It is. So when a fruit fly is starved, an internal state, Its brain chemistry actually changes. Neuropeptides are released that alter its sensory processing.
So the hungry fly literally smells the world differently than a full fly.
Yes, it becomes hypersensitive to food odors. It ignores everything else, potential mates, interesting lights, whatever. It goes into pure exploitation mode. It needs food now.
Hangry mold. We've all been there. Tunnel vision.
Exactly. But when that same fly is satiated as full, those neuropeptides shift. It stops caring about food smells. It starts wandering. It becomes
It
curious
goes into exploration mode.
just to map the area.
Okay.
And the internal state is the switch. It's not random. The body tells the brain what to prioritize.
And the authors propose using this exact mechanism in AI. They call it neuromodulation.
Yeah. It sounds complicated, but you can think of it like adjusting the bass and treble on a stereo.
Okay.
A neural network has weights and biases, right? How strongly neurons connect. Neuromodulation acts like a volume knob that adjusts the gain or sensitivity of certain pathways
Yeah.
based on that internal state.
So if the AI's energy variable is low, neuromodulation kicks in and cranks up the sensitivity to anything that looks like a charging station.
Yes, it's like hyperparameter tuning on the fly.
Yeah.
Instead of a human engineer stopping the robot to reprogram it, the robot's own internal anxiety about its battery changes how its brain processes the camera feed.
It dynamically switches strategies.
Okay.
That is true adaptivity.
And it solves that catastrophic forgetting problem we mentioned. The AI isn't overwriting its brain, it's just shifting its focus. It can have a hungry mode and a curious mode, all existing in the same network, just triggered by context.
It moves from being a narrow specialist to a generalist.
Exactly. And this all connects to a much broader theoretical framework mentioned in the paper, the free energy principle.
Okay, the FEP. We've touched on this before. It is notoriously dense. How does it fit here in plain English?
Well, in simple terms, the free energy principle suggests that all living things are driven to minimize surprisal.
Surprisal, not like a birthday party, but statistical surprise.
Correct. Information theory surprise. Unexpected states. If you're a fish, being out of water is a high surprisal state. It's improbable and it's dangerous. You want to stay within the states you expect.
So minimizing surprisal is just staying in your lane to stay alive.
That's a good way to put it. And the authors view the internal state as a universal and valuable context. It's universal because your body is always with you. And it's valuable because keeping it stable, minimizing that surprisal, is the definition of survival.
Okay, so this isn't just theory. The paper brings up a critical use case for this. Robots in space.
Yes, space robotics, the perfect testing ground.
Because if a robot is on Mars, there's no IT guy.
Exactly. Imagine a rover deep in a crater. The signal delay to Earth is 20 minutes each way. If it trips and damages a wheel or its battery starts overheating, it can't wait 40 minutes for Houston to notice.
It needs to know it's hurt instantly.
It needs to monitor its own health structural integrity, battery levels, heat. This is known as integrated system health management, but usually that's just a dashboard for humans.
A red light blinks in Houston and someone spills their coffee.
Right. But with interoceptive AI, the robot would feel the pain of the overheating battery directly.
And that pain would be a negative reward.
It would increase the distance from homeostasis, so the robot would autonomously change its mission. It might stop climbing, find shade, and go into a low power mode. Not because of an if-then statement, but because its internal drive for thermal balance overrode the external command to explore.
That is incredibly cool,
Yeah.
but it's also a little bit eerie.
Eerie how?
We're using words like pain, anxiety, needs. What does this mean for the concept of emotion? Are we accidentally building feelings into our toasters?
That's a huge question. And the authors go there. They suggest this framework could be a computational model for effective neuroscience.
Affective meaning feelings,
Yeah.
emotions.
Yes. I mean, what is an emotion really? Many neuroscientists would argue it's a high-level interpretation of a low-level bodily state.
You feel afraid because your heart is racing. You feel hangry because your glucose is low.
The feeling is the brain's shortcut to force you to pay attention to the body.
So if an AI is regulating internal stress variables to survive,
Yeah.
then it has a computational basis for feelings.
Mm.
It bridges that gap between cold calculation and the urge to survive.
Mm-hmm.
The paper suggests these internal reward signals are the primitive precursors to emotion.
It's not just simulating sadness, it's experiencing a negative deviation from its required state. It is mathematically unhappy,
Exactly. And this also helps with something called the stability-plasticity dilemma,
which is,
the balance between having a stable identity and being able to learn new things. If you're too plastic, you fall apart. No core. Too stable, you can't learn.
And the internal body is the anchor. Yes. The internal state provides the stability. I am this thing that needs to keep its battery charged. That's the anchor that lets the external-facing part of the brain be incredibly plastic and creative without drifting away.
Okay, so looking at the big picture, we're moving from AI as a tool that processes input to AI as a system that maintains its own existence,
From doing what you're told to doing what you need to survive.
which is a massive leap. But I have to ask, what about the ethics? If we build machines that can suffer from low battery or feel stress, what are we doing?
They do touch on it briefly. They acknowledge that if an AI has internal drives and needs, our relationship with them changes. We aren't just users anymore. We become caretakers, maybe.
And if an agent has a drive to self-preserve and we order it to do something dangerous,
You might say no. It would have to weigh the external command against its internal survival drive.
I'm sorry, Dave, I can't do that. My cortisol levels are through the roof.
Laughs slightly. Essentially, yes, it opens a Pandora's box. But the authors argue it's a necessary step for robust intelligence. You can't have the survival instinct without the potential for stress.
So to get the real adaptive smarts, we have to give them feelings.
We have to give them a life, or a simulation of one so deep the distinction starts to blur.
So to recap,
Hmm?
we started with the brittle AI versus the resilient cat. The missing piece is interoception. We saw how to code it using factorization, a Markov blanket, and internal rewards. We learned how neuromodulation copies the fruit fly to switch between exploring and exploiting. And all this could lead to robots that can survive alone in space.
That's a solid summary. It's a shift from extrinsic goals to intrinsic needs.
Is there one last thought from the source material that really stuck with you?
There is. They quote Claude Bernard, a physiologist from the 19th century.
What did he say?
He said, "The stability of the internal environment is the condition for the free and independent life."
Wow, the condition for the free and independent life.
Think about that. We think freedom is about doing whatever we want externally. But Bernard and these researchers are saying you can only be free if you're stable inside. If you rely on someone else to charge your battery or tell you when to eat, you aren't really free.
That is deep.
It implies that until we give AI the burden of maintaining its own internal stability, it can never be truly independent. We've been trying to code intelligence, but maybe we should have been trying to code struggle, because it's the struggle to maintain that balance that creates the self.
So if the stability of the internal environment is the condition for a free life, have we just written the recipe for machine free will?
It's a question worth pondering.
On that slightly terrifying but exhilarating note, we're going to wrap up this deep dive. Thanks for listening, and we'll see you next time.